Today we're going to talk about temperature and heat, or temperature and heat energy. People use these words as if they're interchangeable, as if they mean the same thing, but they don't. They're related to each other, and later on we'll find out how they're related. But temperature and heat are not the same thing. Let's get some definitions down, and then we'll talk about what that all means. Temperature can be thought of as the degree of hotness of an object. We're not talking about your girlfriend here. We're talking about how fast are the particles that make this object up moving. So everything is made up of little particles. Mostly we can't see these things. They're called atoms, or ions, or molecules, teeny tiny invisible particles because they're too small for us to see. But they're not stationary. They're all jiggling around constantly, moving around back and forth, back and forth, back and forth. When it gets cold, they jiggle around slow. When it's hot, they jiggle around faster. And so the average of all the kinetic energies, KE, or energy of motion, that's what temperature really is. Heat is the total amount of all the energy that's stored in the tiny, rapid movements of all those particles. So what's the difference between temperature and heat? Because they're both related to these movements of the particles. Well, here's an analogy that might help understand this. Think about two states. I looked up some data for Maryland and California. And here's what I found out. In Maryland, the average person has an income of $69,272 at the time I'm recording this. In California, the average person has an income of only $58,931 per year. Now you might think by looking at this that Maryland has more income than California. But this is just an average. It doesn't tell you the whole picture for the whole entire population. In fact, when you look at the fact that California has over 36 million people in it, whereas Maryland has only about 5.5 million people, and then you take a look at how much all those people together earn, Maryland is way poorer than California. In fact, Maryland took in $3.9 trillion the same year that California took in $21.6 trillion. Why? Because even though the average person in Maryland earns more, there's way more people in California. That's what heat and temperature are like. Temperature is like the average. That's like the 69,000 versus the 59,000. But the total amount, the 3.9 trillion versus the 21.6 trillion, that's energy or heat. It's the total. It's not just the average. If an object gains heat energy, its temperature will go up, but they're not the same thing. Here's an example. These two pictures show things that have the same temperature. A match made of a piece of pine burns at the same temperature as a whole forest fire full of pine trees. However, those things do not release the same energy by any means. The forest fire releases way more energy than the match does. Well, how do we measure temperature? We've already talked about that. That's units of kelvins, or degrees Celsius or degrees Fahrenheit more commonly in the non-scientific world. How do we measure heat? Well, since heat isn't the same as temperature, we need a different unit. There are several units. These are some of the most common and easy to understand ones. The calorie is the amount of energy that's needed to take a gram of water and raise its temperature by 1 degree C. You'd have to add that much energy, a calorie. So here's what we're talking about. This beaker has got a gram of water in it, and there's a thermometer sticking in there. I put a burner underneath it, and now I'm going to add energy to the water. Watch what happens. As I heat it up, the temperature of the water goes up. When 1 gram of water has increased its temperature by 1 degree C, well, that means 1 calorie of energy has been added. Another unit is also called a calorie, but the difference is it has a capital C. This is the calorie that is used by people who measure energy in food. It's also called a kilocalorie because it's 1,000 little c calories. So here's what that would mean. If I have a beaker of water that has 1,000 grams in it, that would be a liter, and I make its temperature go up by 1 degree C, I would be adding 1 big C calorie. So if you think about a candy bar that has 250 calories in it, that's 250,000 of the little c calories. That's enough energy to make a liter of water go up 250 degrees. Another unit of heat energy that's fairly common is the joule. The definition of this unit is more suited to physics, but it's a commonly used unit, and there's a conversion. 4.184 joules is the same thing as 1 calorie, 1 little c calorie. So that's a conversion factor that you could use in proportional thinking to go back and forth between these units. We know that temperature and heat are related. There are two concepts we can use to tie them together, both mathematically defined words or terms. One is heat capacity. The relationship between the heat an object absorbs and its temperature change is called heat capacity. Objects that have a high heat capacity can absorb a lot of heat without much of a temperature change. Mathematically, here's how we define this. Heat capacity is Q, which stands for heat or heat energy, divided by this term here. Now this has got two parts to it. This is a Greek letter, delta. And delta means change, almost always, in science. So change in T, and T, you might guess, is going to be temperature. So heat capacity is a mathematical expression. Take the heat, divide it by the change in temperature, and you get the heat capacity. Here's an example problem. If a bucket of water from Lake Superior absorbs 1,000,000 joules of energy, its temperature goes up by 12 degrees C. What's the heat capacity? Well, using our definition, heat capacity is equal to heat, which in this case is 1,000,000 joules, divided by the temperature change, which in this case is 12.0 degrees C. When you work out the numbers, here's what you come up with. 83,300 joules are needed to make every degree C of temperature change. A joule is a pretty small unit, so that's why the number seems really big. Now here's another problem. You try and work this one out. This is asking if Lake Superior, the whole lake, absorbs 1,000,000 joules of energy. Its temperature goes up by 1.99 times 10 to the negative 15th degree C, which isn't much of a temperature change. What's the heat capacity of Lake Superior? All right, so heat capacity is Q, which in this case is 1,000,000 joules again, divided by the temperature change, which is not much, 1.99 times 10 to the negative 15th degrees C. That's what I get when I work this out. 5.03 times 10 to the 20th joules per degree C. So compared with our bucket of Lake Superior water, Lake Superior itself, as you might have guessed, has a much higher heat capacity, 500 billion joules, to make Lake Superior go up by a degree C. Sometimes we want to know not about how an object behaves, but how a certain amount of a substance behaves. So we can make predictions based only on what the substance is that doesn't depend on how big it is. So that's what specific heat is, the relationship between how much a certain amount of a substance absorbs and the temperature change. So here's our definition. C is the symbol we use for specific heat. Q, just like in the last equation that we saw, is heat or heat energy. Delta T is change in T or change in temperature. And now we have a new term, and that's M, and this stands for mass. So now we have two things to consider in the denominator. How big is it, and how much did the temperature change? Okay, here's another example using Lake Superior. A bucket of water from Lake Superior has a mass of 20,000 grams, and it absorbs 1,000,000 joules, and its temperature goes up by 12 degrees C. What's the specific heat of the bucket of water? Well, specific heat is Q divided by mass times change in temperature. Heat, mass, change in temperature. So the heat here is 1,000,000 joules, just like it was in the last problems. The mass is 20,000 grams, and the temperature change is 12.0 degrees C. Now when we look at the units, nothing cancels out, so we have this three-part unit. It's joules per gram per degree C. When I do my arithmetic, here's what I come up with. 4.16 7. So for every gram of water in the bucket, to go up a degree C, I have to add 4.17 joules. It's a similar problem. This is not for the bucket, it's for all of Lake Superior. Has a mass, you can imagine, is going to be huge, 1.21 times 10 to the 20th, which is a little over 100 billion grams. Absorbs 1,000,000 joules of energy, and the temperature goes up 1.99 times 10 to the minus 15th degrees C. What's the specific heat of Lake Superior? Well, again, specific heat is Q divided by mass times temperature change. So Q is 1,000,000 joules. The mass of Lake Superior, it says here, is 1.21 times 10 to the 20th grams. And the temperature change is 1.99 times 10 to the negative 15th degrees C. Same unit as the last problem, joules per gram per degree C. And the number, well, that's also very similar to the last problem. Even though this is for all of Lake Superior, and the last problem was only for a bucket, we come up with pretty much exactly the same answer. And here's why. It doesn't depend on mass. Huge amount of water, small amount of water, on a per gram basis, it has the same ability to absorb energy. Specific heat, then, is independent of size, which is not true for heat capacity. Let's work through this example problem. This will give you a good idea of how you can analyze a problem and use the relationships that you've learned to solve these problems. I mean, without a strategy, this looks like it might be quite difficult. Story problems usually are. But a strategy that we'll use here is just analyze the problem and write down the symbols that we know that come from equations as we go through. A 4-gram piece of glass. Okay, grams is mass, so I'm going to label that M, because M is mass in the equation that we learned. Was heated from 0 degrees C to 41 degrees C. Okay, so that's a change in temperature. So that means 41 degrees C is the difference, and that's delta T. Change in temperature is delta T. As it absorbed 32 joules. Well, joules, that's a unit of heat energy, so that's Q. What is the specific heat of the glass? Well, specific heat is C. So the question is, what is C? I know Q, I know delta T, I know M. Here's the relationship between all these things. C is equal to Q divided by M times delta T. So Q is 32 joules. I'm just plugging in numbers now. Divided by the mass, which was 4.0 grams. And that's times the change in temperature, which was 41.0 degrees C. If I analyze my units, nothing cancels, so I have joules divided by grams per degree C. I have 2 significant figures in this number, 2 in this number, and 3 in this number. So that means I have to round my answer to 2 significant figures. Well, when I do that properly, I end up with 0.20 joules per gram per degree C. Here's another problem. It says how much heat. So as I'm analyzing this problem, here's what I'm doing. How much heat means that's a question, and the question is about heat. Q is, I don't know what. How much heat would have to be added to 2.0 grams? Okay, there's an M. Grams is mass. Of the glass in the last problem, okay, so here's what I know about that. In the last problem, we determined specific heat was 0.20 joules per gram per degree C. For it to increase in temperature, okay, that's a temperature change from 41 to 70 degrees C. So this represents my change in temperature. And if I subtract 41 from 70, I get 29.0 degrees C if I round to the right decimal place. All right, what do I know? M, C, and delta T. What don't I know? Q. Here are a couple strategies. My equation says C is equal to Q divided by mass times delta T. Now, you can do a little algebra on this equation. Since I'm trying to isolate Q, that's what I'm trying to solve for, I want to get that alone on one side. I can do that by multiplying both sides by mass times delta T. And when I do that, mass times delta T cancels on the right-hand side. So what was on the right now is Q. That's isolated. What's on the left was C times mass times change in temperature. And now I just plug my numbers in. So Q is my specific heat, 0.20 joules per gram per degree C, times my mass, 2.0 grams, times my temperature change, 29.0 degrees C. Here's what happens to my units. Grams aren't there anymore, they cancel out. Degrees C, same thing. I should have two significant figures in my answer, and it comes out to 12 degrees C. Here's another way we could do this. This equation, if you're not comfortable with algebra, could be modeled this way. If we think about Q on the top, mass, specific heat, temperature change on the bottom, this makes a little device that if you cover up the value that you're trying to find, this little device tells you what to do with the remaining variables. So in this problem, we're trying to find Q. So if I cover up Q, it tells me take mass times specific heat times temperature change. And that's what the algebra did too. So this is a way to short circuit the algebra. The horizontal line means divide by. The vertical lines mean multiply by. Try this one. So let's go through and analyze the problem. 50 joules, that's Q. The piece of glass in the last problem, okay, here's what we know about that. C is 0.20 joules per gram per degree C. Temperature went up from 20 degrees C to 25 degrees C. Well, that's a temperature change, and it's 5.1 degrees C. What was its mass? There's the question. Mass equals question mark. Let's try that little device. It says Q over M times C times delta T. What we're trying to find now is mass. If I cover that up, it tells me mass will be equal to Q divided by C times delta T. If you're comfortable with algebra, you can come to the same conclusion by doing a couple of little steps of algebra. Let's plug in the information. Q, 50 joules. Specific heat, 0.20 joules per gram per degree C. And temperature change, 5.1 degrees C. Degrees C cancel out, so do joules. I'll end up with 1 over grams, which is just grams. And that's good because it's mass. Every measurement has two significant figures. My answer should as well, and I rounded to 49 grams.